This video illustrates the paper on passive inverse dynamic control using a global energy tank for torque control humanoid robot in multi-contact. It contributes toward the adaptation of the passivity method of Dietrich et al. For inverse dynamic using a global energy tank. We will first recall the theory of the passivity used in the paper. Then it presents the result of our simulations, one on contact force task and one on a locomotion scenario. The passivity analysis consists in exhibiting a potential function, h dot, which will remain lesser and equal than the flow of energy of the system, that is to say the input times the output of the system, here the velocity and the torque. So we will exhibit a function h dot, which will prove the passivity of the system controller and robot. Indeed, the subsystem robot environment is passive with respect to the velocity and the external torque. To monitor the energy flow of the task, we add a global energy tank to our inverse dynamic quadratic program. Thus, the formulation is composed of two layers. The first one will compute the derivative of the potential function, which contains the derivative of the energy tank. We will retrieve the coefficients alpha, beta, and gamma, which will then be used in the second layer to penalize the tracking of the task function used in the quadratic program formulation. Moreover, we use the derivative of the potential function in the constraints of the quadratic program so that we have the inequality that will hold at any time. In the simulation, we have the robot which will create a contact between a tool and the surface. Here it's a cylinder and a block in Gazebo, and will apply a force of 30 Newton. Our problem is composed of 6 tasks: the fit position, the center of mass position, the force applied by the hand, the waist orientation, the posture of the robots, and the angular momentum regularization to 0. First, the robot applies a force of 10 Newton, and here you can see the oscillation due to the slippage on the contact because of the contact of Gazebo. These oscillations are dependent on the way we put the tool on the surface, so it's not really relevant here. We can see two peaks in the energy and force tracking. One represented here by the red box due to the removing of the block, and one in purple due to the removing of the force task. Following this removal, the energy in the tank is taken by the posture task. Indeed, the robot returned to its initial position, and so the arm of the robot goes against the gravity. The second scenario is a walking simulation, where the robot walks 1 meter forward on flat floor with 20 cm steps long. The set of tasks is the same as the previous simulation without the contact force one, and adding fit motion task during single support phases. At the beginning of the simulation, the motion is slow because the center of mass is moving in quasi-static. Thus, it leads the tank to be emptied, leading the beta parameter to decrease to 0. It leads to oscillation in the other parameters, which make the robot oscillate as well, because these parameters beta and gamma are used in the tracking errors formulation. Except from this concerning beginning, the robot achieves the walking motion without trouble, with a good tracking of the reference trajectories, as can be seen in the figures. This motion can be seen as a repetitive sinusoidal one. The increases of the energy tank correspond to the motion of taking the center of mass in the middle of the support polygon and thus the feet in double support. Reciprocally, the tank energy decreases when the center of mass reaches the edge of the support polygon above the supporting foot. To conclude, our passivation scheme has been successfully implemented and tested in simulation on Gazebo, on the robot TALOS, in simulations on a multi-contact scenario and a locomotion one. This work is supported by the cooperation agreement Rob for Fam.